side too. I've been a tail long enough.
Now, if you guys talk to me.
Wait, what? Everything we say is on.
Yeah.
Good thing Ross is over there.
Yeah, Ross, the top of your head is just going to be not too much.
It's your haircut that's going to be featured, so just hold up a sign that said it did this hair.
I know. Do it for the camera.
Do it for the camera. Do it for the walls.
It's my freaking pleasure to spend it.
All right.
Spicy chicks.
Let's get started here. So on Monday, we were going over your homework 317, and we ran out of time to complete it. So let's pick up where we left off there. And what we were asking is, what happens if we have the option to buy 500 additional pounds of steel at $2 a pound? Should we buy it or not? And so what we started looking at on Monday is we compared these two lines right here, where they intersect. If you remember, we basically have something like we have a constraint like this. Let's call this the first constraint. We have a second constraint and a third constraint. And we have a situation that looks something like this. And so when we move this from 40,000 to 40,500, we're going to preserve this slope right here. And our question that we were asking is whether we are on this side of constraint number 3 or on this side of constraint number 3. Because if we're on this side of constraint number 3, the dual that we compute isn't valid. And so what we said is, what we did is we computed this intersection point right here. And we discovered that happens when B equals 1050 and W equals wait this down correctly. 1091 point something and 763 point something. So we know where that is. So now what we can do is we can figure out where this green line would be if it also intersected at this point. By putting these values, B and W, back into this equation right here, the left-hand side of this equation. Not the full equation, but the left-hand side of the equation. And if we did that, we would see that the right-hand side of that first equation would end up around 40,909 point something. So that means because we're only bumping it up to 40,500, we're going to end up just short of this intersection point right here. Which means the dual that we compute then is valid. If this intersection point was over here, we'd have to do it piecewise. We could compute the dual up to here, and then we would have to figure something else out after that. But since the full extent of that works, we're good. So now we can do another intersection, right? We're doing a bunch of line intersections here. Where that moved line is, where it intersects the new point with this second constraint right here. And that point, right there, let me keep it in green, so that's where B equals 1050 and W equals 780. Okay, so if we buy the extra 500 pounds of steel, that's what we'll have. We can now plug these values in to our objective function here to see how much money we could make, what our profit would be if we had that much steel available to us. And we get a profit of $428.4 thousand. Yes, sir.
I understand how we got the ones in red, the B and W points in red.
Yeah.
Where did the B and W in green come from again?
The intersection of this new constraint 1, because this point right here is what it was with
Okay.
the 40,000. This is what it is with the 40,500.
Oh, okay.
Because we have 500 more pounds of steel available to us. So it's going to change how many of each unit we want to produce. Right? That's one of the big differences between when we examine the right-hand side of our equations changing from these coefficients changing up here in our objective function, which we looked at earlier. Here, the optimal solution won't change. Here, the optimal solution is guaranteed to change because we're moving these constraints. Yes?
So what was the point of finding the red B and W? Because the new profit is in the green, right? So then why did we find the red stuff?
We needed to make sure that this green line didn't go beyond that. Because if it did, we wouldn't be, and we computed where that green line, if it went beyond here, we wouldn't be computing a value that was legal. Because we'd be forgetting about this constraint number 3 here. So it's a check on us to make sure we don't get too much steel that overwhelms some other constraint. So that's why we had to check to make sure that that point was within our margin of moving that right-hand side. Okay? So we're almost done. Now that we've computed our profit, how do we compute our dual again? Right, so it's the change in our objective divided by the change in the right-hand side. Right, so what's our change in our objective? How much did we improve our objective by? So, and how much did we move our right-hand side by? We increased it by 500, right? So that means that our dual in this case is, and this is pounds, is $8.80 per pound. So we expect for every pound of steel that we buy to increase our profit by $8.80. Up to this point, this red point here. So up till 909 pounds. Then the dual would be no longer valid. Yes?
So since we're moving the dotted line along constraint 2, would that be the dual for constraint 2?
No, it's the dual for constraint 1.
Okay, so it's what's moving.
It's the one we're moving,
Okay,
not the one we're moving along.
okay.
Because you could conceivably have multiple binding constraints that you move along
Okay.
in a multi-dimensional
Right.
example.
So if we had found that the changing constraint went beyond that point, we would have done a different.
Yeah, so we would have just computed up to that point.
Okay.
We would have computed the change up to that, and that's what we would have said is valid. And then any additional thing that we add above that. So let's make, rather than some hypothetical, let's make it clear. Let's say instead of having 500 pounds of steel available to us, we had 1,000 pounds of steel available to us. Okay, so now it wouldn't be 40,500, it'd be 41,000 right here. Okay, that now exceeds this point of 40,909. Okay, this dual that we computed right here earlier, so we don't have to recompute it, is valid up through this 909 pounds. So you would say that you would get $8.80 per pound for the first 909 pounds. But for the next 91 pounds, you wouldn't make $1 profit more. Because your constraint would actually be out here, and our feasible region is right in here, and when you push it out, it's only to right here. It can't go out to this line right here, because this other constraint right here is blocking it. So every pound that you get more, it's going to keep moving this constraint outward, but you're not going to make any more profit because of the other constraints becoming binding. So we would only want to take, if we could, we'd only want to take 909 pounds of steel. Now, if, let's say they only sold it in lots of 1,000, well then what we'd have to do is say, well, for the 909 pounds of it, we would make $8.80. For the remaining 91 pounds, we would make nothing. It would just be wasted steel for us. And so you would compute that $8.80 times the 900 pounds that you made the profit, and compare that to the $2 per pound for the 1,000 pounds that you had to buy overall. And in that case, it would still be valuable to you, right? Even though you had some wasted steel, it would still be a valuable process. But if they sold it in lots of 2,000 or 2,500, there would become some point where it wouldn't be worth buying that large lot, because so much of that steel would be excess capacity that you wouldn't be able to use. And it's the dual that tells us how much we make and at which point that cutoff exists. All right? So the answer to, what is this, part B or C? I don't remember, I don't have it marked on my notes. Part C, thank you. B is, yes, you should do it, because you'll make $8.80 per pound while only paying $2 a pound, so you make an additional profit of $6.80 for each of those 500 pounds of steel that you use. All right? So part C asks if we should, I think, increase the assembly minutes, which is this third constraint here, right? What's the answer? We don't even have to do any calculation here. Should we add assembly minutes?
No.
Why not?
Because it's not binding.
It's not binding, so adding more is just going to make it even more not binding, right? So that's a really easy one to look at. Part D then asks, what happens if we reduce our profit, right? If there's a competition and we have to reduce how much we sell our product for. We need to see if we still should make the same amount, right? So now, we're not looking at the right-hand side anymore. Now we're looking at the coefficient in our objective function. So we're saying this is what we think the optimal solution is, where that intersection is of constraints 1 and 2 that are binding. Will that still be true if this gets reduced down to $175 rather than $200? So, how do we answer that question? How do we know whether we should still make the same number of B and W units? Slope of what? Okay. So we have to look at those three slopes, right? So what is the slope of this binding constraint right here? It's going to be negative 20 over 25, right? Which is negative 4/5. What's the coefficient of this? Right, and the slope of our new objective function is going to be, which is negative 5/8, I think.
I got part of it. I like that. Stop.
Which still is between those two slopes. All right? So that's one way you could have done it. The other way that you could have done it is if you remember that you want negative 4/5 is less than or equal to and then we'll keep our W coefficient fixed, right? We're not changing that. So that's 280. And then you solve for negative C sub B and see the range of values that C sub B could be by multiplying both of these sides by 280. Or let's do it by negative 280 so we get rid of the negative sign. Okay, and then you would get 112 is less than or equal, which is less than or equal to 224. And so we get the range of our coefficient here as being between 112 and 224. We see that 175 is between that range. And so it's the same math that's happening, it's just looking at it from a different perspective. Both of us tell us that this is going to give us the same production results. All right, questions about that? Last question then, excuse me, was, I had the answer, but I had the question. What was the question real quick? For part, what is this?
For E,
The last part.
if the available manufacturing time is increased by 500 hours, will the dual price for the manufacturing time constraint change?
Okay, so the manufacturing time constraint is which one?
It's the second.
It's this one, right? So it's asking if we can increase it by 500 hours. What units is this in?
Minutes.
Minutes, so we need to convert 500 hours into minutes. Right, what is 500 hours in minutes? 30,000, okay? So, so it turns out that number 2 is binding until it goes all the way above constraint number 1, which would be, if we finish this diagram here, at the y-intercept of constraint number 1. That's when it would be binding. So if you compute where the y-intercept of constraint number 1 is, then you know how big constraint number 2 needs to be before it to be non-binding. And it turns out that that is obviously 0 on this, or b equals 0. And for W, it is, let me look, 1600. Okay? So, if constraint 2 ends up, if we move constraint 2 by increasing this by 30,000 minutes, we're going to move it up, right? And what we have to check is, if we do that, are we above or below this line right here? So, if you plug in 0, 1600 into this left-hand side, you get 40 times 0 plus 100 times 1600, you get 160,000. That's where constraint 2 would have to move in order to go above this constraint line right here. And we're only adding 30,000, which would move this only up to 150,000. So constraint 2 would still be binding when we add 500 hours, and since it's still binding, that means that the dual is still valid. Questions about 317? All right. We're temporarily going to stop talking about sensitivity analysis. Temporarily. Because, as you can see, it's starting to get pretty rigorous. Not rigorous. It's a lot of busy. It's going to turn into a lot of busy work really quickly. So what we need to do is let the computer start figuring out what the dual is for our problems. It needs to figure out what our optimum solution is, and it needs to figure out what the range of our valid constraints can be in our objective function. And so what we've been doing now is thinking about our solutions graphically. But that's not going to scale in either number of variables, right? We can only draw two-dimensionally. And it's not going to scale in constraints. It's going to be, or if we've got something that looks really close, it can be really hard to tell visually what the solution is. And we would like to know what the right solution is. So we need to come up with a more methodical solution to these problems. So we're going to jump to chapter 17, in your textbook to talk about the simplex method. All right? And we're going to see how the simplex method works. And it's very algorithmic, and that's great for a computer. A computer can do algorithms really well. It's going to temporarily insert a little bit more pain into your life. Sorry. Until you understand how the simplex method works, and then we'll fully convert over to letting the computers do the work for us. Once they do, then we can go back to doing more complex models and asking more sophisticated questions about what the dual says and the sensitivity analysis with the more robust models that were available to us, because we don't have to depend on just a two-variable solution. All right? So, let's take a completely artificial example here to start, because we want to focus on the math, and we're going to ignore the meaning for right now. We'll get back to the important thing as we understand how it works. So let's say we're going to maximize this objective function right here, 3x plus 4y, subject to 2x plus y is less than or equal to 8, 2x plus 2y is less than or equal to 10, x plus 2y is less than or equal to 8, and our logical constraint. Okay? Now, we already, I should have done this. We already made one step in this process earlier in the semester by switching to standard form, right, and inserting our slack and surplus variable. So help me out here. How do we transform this into standard form? What do we do? Plus S1.
And then choose that.
And, no, they were all less than or equal. Okay? want to be clear about this, these are now variables. So we need to represent them in our equation. It's been understood up till now. But we now have not just 2 variables, x and y, but we have 5 variables, x, y, s1, 2, and 3. And the issue that we now have is, and we've seen this with our graph, is there is not one solution to this equation, this set of equations. Because we have more variables than we have equations. Okay? When we did our systems of equations and we solved them at the beginning of the semester, we had the exact same number of equations and variables. And so it was really easy for us to solve them. Easy relative term, right? We had a way to solve them because we only had an exact match between the number of variables and the number of equations. So what I want to watch what happens with our solution here, so I'm going to draw a graph here. And I'll go quickly, I promise. So, okay, so our first one, if y is 0, x is 4, and if x is 0, y is 8. All right, our next one is going to be 5 and 5, right? And our last one is going to be x is 8 and 4. All right. So now this is our graphical solution that we've been doing so far. Over here, we're going to do a numeric solution and show how the graphical solution and the numerical solution relate to each other. So here's what we're going to do. We know how to solve a system of 3 equations if we only had 3 variables. But we have 5 variables. So here's what we're going to do. We're going to take an initial guess at 2 of the variables, and then we'll only have 3 variables left, and we'll solve it for that. Okay? So, we don't know what values of x and y our solution is going to be, so our initial guess is that we're going to start here at x and y equals 0. Okay? Does that make sense? Do we expect this to be the final optimal solution? Probably not. But it's a starting point. Okay? And so if we did that, then these 2 variables would be 0. We already know what S1, S2, and S3 are going to be, right? That's going to be really easy. Okay? Now, what we're going to do is we're going to have to move towards our final solution. And what we're going to do is we're going to say, well, this wasn't a really good guess. We would like to improve it by switching our guess out a little bit. And instead of saying that x and y are going to be 0, we're gonna either go up the y-axis or out the x-axis. And we need some help figuring out which one we should do. Okay? And the answer is we should go whichever way is going to most increase our objective function. And that's what we're going to do. So this is already starting to get complicated, so we're going to introduce what we call our tableau. Yeah, I know. That's as French as I get for my speaking. Sorry. Okay. The tableau is just a representation of this, but what we're going to do is we're not going to constantly write our variables and the plus signs over and over and over again. We're only going to write the coefficients for them. And we're just going to know that the first column represents x. The next column represents y. The third column represents S1, S2, and then S3. Okay? So we're just trying to make it quicker for us to solve the simplex steps. But it still is this objective function and all of these equations. But we're just going to write down numbers to represent that. So the first thing we're going to do is we're going to write down our coefficients for our objective function. That's going to be the top line of our objective function right there. Okay? And maybe we put our variables up top here so it's clear which one go with which. We're going to make a column up here. It's called the basis. So for those of you who've taken linear algebra, this has that same meaning in this vector space. All right. This basis is the set of variables that we don't know the value to. Okay? So what was our initial guess? Which variables did we guess? X and Y. So which variables belong in our basis? S1, S2, and S3, because those are the ones we don't know, because we guessed the other ones. So initially, these would be our S1, S2, and S3 variables here. Okay? Then what we're going to do right here, this isn't totally necessary, but it makes computation a little bit easier, is we're going to copy directly out of here the corresponding coefficients. It's a straight copy. So we look at S1, we find the S1 variable, and we copy it over. We look at the S3, we find the S3 variable, and we copy its coefficient over right here. Okay, so you don't technically need that number in two places. But it's just a lot easier to do the math when you've got it aligned in this way right here. Alright. Below here, these are the coefficients of the constraint. Okay? And then right here is the right-hand side of the constraint. And then down here is our current solution. Then we're going to make one more line here. We will call this ZJ, and we will call this CJ minus CJ. Okay, we'll see how those get computed. This is the format that we're going to repeat over and over and over again for our tableau. Okay? So I want you to, this is kind of the map, understanding what is going to happen with all these numbers right here. Yes?
So you put the coefficient of those three variables from the objective function in the second column,
Yes.
but they also have coefficients in the constraints, so do you
Yeah.
put those there too?
Yes, so let's do that. I'll go right here. If this goes up. Sorry. All right, so let's do our initial setup. Let's just do it in the same order that it is in our objective function right here. We have x, y, s1, s2, and s3. And what are the coefficients of our objective function for x? Y, s1, s2, and s3.
0.
Okay. So we already said we know what variables are going to be in our initial basis. What were they? Okay, and what did we say we do here? Where do we get the values from here? We copy them straight from our top line, right? So what's the coefficient of the objective function for S1?
0.
And what's the coefficient for from our objective function of S2?
0.
And our coefficient from our objective function of S3?
0.
All right. Now we need to fill this in. So we're going to take the first constraint. What is the coefficient for our x?
2.
What's the coefficient for our y?
1.
What's the coefficient for our S1?
1.
What's the coefficient for S2?
0.
And our coefficient for S3?
0.
And what is our right-hand side for that constraint?
8.
Okay? So you can see what we're doing here. What should be the next line? What's the coefficient for x?
2.
Y?
2.
S1?
0. 1. 0.
All right, and the final one.
1. 2. 0. 0. 1.
Okay, before I go on, yes?
Is it just a coincidence that that looks like a solved matrix?
It is not a coincidence. And that's exactly what I wanted to point out. Our S1, S2, and S3 variables here have to have coefficients that basically represent a unit vector. Okay, so each one of them is going to have a 1, 0, 0 pattern, and they have to have ones in different lines. Okay? That is always going to be true. So if we have a variable over here, we need to make sure that it looks like this. So if we take out one of these variables in a second, and we put in an x or a y, we're going to have to modify this, make this thing to look like this pattern for the variables that are inside our basis. Okay, and we need to keep making sure that that pattern holds. And we'll just keep doing that until our algorithm tells us to stop. No, they do not need to be right in a row. They will move around. You just need to make sure that they preserve this pattern. Okay? Remember, this is representing an equation. 2x plus y plus s1 equals 8. Right? It is this equation right here. It's just, we don't want to keep writing those variables and those plus signs over and over and over again. This is just to save us time. This is an equation, and these are the values that are going to have a non-zero value in our solution. Alright? We're always going to have, in this case, because we have three equations, we're always going to have two variables that are equal to 0. And we're going to have three variables that are not equal to 0. And that 3 comes from the fact that we have 3 constraints. If we had 10 constraints, we would have 10 variables that were non-zero, and all the rest would be equal to 0. Okay? That is what allows us to solve these equations, because we have to have an exact number of variables with the number of constraints that we're trying to solve. Okay? So, let's think about what this 2 right here means. Okay, we said that we might want to increase x, or we might want to increase y. What this 2 means is that if we do increase x, that's how much we have to decrease S1 by. Okay? So if, because right now, we have 2x plus y equals 8, need to include S1, plus S1 equals 8. Right now, x equals 0. So if this gets bumped up to x equals 1, we know the current value of S1 was 8. Because we increased x by 2, we're going to have to decrease S1. It's going to have to move down to 6 for this equation to remain valid. Do you see that? Because we need to keep this as an equality. If we increase x, we have to decrease S1 a corresponding amount. So each one of these numbers here represent how much, if you increase this variable, how much you have to increase that, you have to decrease this variable by in order to keep your equations in balance.
I'm confused on what you mean by current value. Like why
So-
why was x 0?
We just, remember we started with a guess.
Okay.
So we guessed that x and y were 0.
Okay.
So if we want to move x along here, we're going to have to decrease S1 by some amount
Okay.
in order to make that happen. We're also going to have to decrease S2, and we're going to have to decrease S3.
Okay.
All right? Yes?
We just made up 0, 0, right?
We did.
Could
We picked it because it's easy.
Could we pick a different number that was, as long as it's still within the feasible region of graphical representation?
No, because then we would have more than 3 non-zero. Well, yes, you could, but it would result in a really weird basis.
Okay.
Okay? So we're just gonna always stick with 2 non-zero.
Since these three are all surpluses, is there a different way we're supposed to write it so we know when that means a slack?
Well, how does a slack go into the equation?
Minus.
It's a minus, so what's the coefficient?
Negative one.
-1. All right? So we need to be able to, so if we increase x, we have to decrease S1 by 2. If we increase x by 1, we have to decrease S1 by 2. The same with S2. We only have to decrease S3 by 1 right here. So we need to figure out whether we should increase x or y. Okay? So we need, to help us there, we need these last 2 rows. Oh, let's fill this in. What's our current solution for our objective function? 3 times the value of x, which is, results in, plus 4 times the value of y, which is,
0.
So we still have a sum total of 0. Plus 0 times, I don't even care what that is, plus 0 times, plus 0 times, right? So our current objective function value is a really wonderful 0 right here, right? All right. And so this is, I'm going to label this z sub j, is how we can compute this. Because what we're going to do is we're going to multiply the value of our variable times its coefficient. So right now, this is all zeros because this is x equals 0 times 3, y equals 0 times 4, s1 equals 8 times 0, s2 equals 10 times 0, and s3 equals 8 times 0. That's why we've got these 5 zeros here. Okay? And this is c sub j minus z sub j. And all we do, if you want to mentally think about it, this row is c sub j. So we just subtract this row from this row. So what's 3 minus 0?
3,
4 minus 0?
4,
0 minus 0?
0,
0 minus 0?
0,
And 0 minus 0.
0.
Now what we're going to do,
I got it. Who's the only one who wins?
because, yeah. it-
Good at simple
C
math.
stands for coefficient. So, and J means which column.
There it was.
Okay, so what we're going to do then is we're going to look at these values here in c sub j minus z sub j, and we're going to identify the largest one, which is 4. So that means what we're going to do is we're going to insert y into our new basis. So y is going to go in here, which means we need to get rid of one of those values, right? Because we can only have 3 possible. This means that a move of y is going to affect our objective function by 4. If we increase y by 1, we'll increase our objective by 4. Here, if we increase x by 1, we only increase it by 3. So that's why we pick 4 instead of 3, because moving y is going to make a greater, each step of y that we make is going to make a greater contribution to our objective function than each step of x is going to make right here. And we want to make the largest possible step that we can. Alright? So we want to stick y into our basis. So now we're going to go back to our meaning of these. Right? When we increase y by 1, we're going to decrease s1 by how much? 1. So for this equation, if we only consider y, how much room do we have to increase y by? Where did you get 8 from?
That's what S1 equals?
That's what S1 equals, right? And since we can, for every increase of x, y, there's a corresponding decrease of S1, we have room for a full 8 units of increase. So this line right here is called Bij over Aij. What you're basically doing is you're dividing this number right here by the corresponding coefficient for the variable that you're changing. So this is 8 divided by 1 here. Okay? Which means 8 divided by 1. Yes, it's a new column. So based on that, what should go in here? What should be the numerator? What should be the numerator? 10, because that's what our right-hand side is. What should our denominator be?
2.
2. Now let's walk through why we get 10 divided by 2. In this case, S2 is equal to 10 with our first guess. So if we want to see how much we could possibly move y for here, we only can move y by 5 units, because every movement of y has to decrease s by not 1, but by 2. So that's why we divide this 10 by 2, because it tells us what our starting variable was and how many units we have available to us to increase it. Yes? Okay, so here, if we only consider this constraint, we could move y by 8. But when we take into account here, this constraint, we can only move y by 5. And then finally, let's look at this final constraint here. 8 and 2 are our numerator and denominator. In this case, we can only increase y by 4. Let's look at our graph right here. Our black constraint. We could have moved y all the way up to here. That's that 8 right there. 8 divided by 1. Okay? The red constraint, that's 10 divided by 2, or 5. And the green constraint is the 8 divided by 2, or the 4. What's the maximum that we can move y? We can only move it up to this point right here. If we move it any further, we go outside of our feasible region. Right? So this division right here represents how much is available for us to move that variable. And so we will get 8, 5, and 4. And we're constrained to choosing this smallest one right here. That's the most we can move y and still keep it within our feasible region.
So is it always the smallest?
It's always the smallest. It's always the smallest of these. It's always the biggest of these. Right? Because we want to move the biggest steps we can, but we're limited how far we can go. So we're going to make a new line in our table here. I'm just going to extend these down here.
351.
And what we're going to do is we're going to say we're going to replace S3 with Y. So our new basis is going to be S1, S2, and Y. Okay?
Oh.
Because we're going to get rid of S3, we're going to, when we move up here, there's no more slack in that constraint. So we get rid of that S3 and we replace it with Y right here. Yeah, we got it completely. So what we're going to pick up here on Friday is how we then incorporate Y into the next iteration of this algorithm instead of S3 here.
Yeah, the last part's gonna be in the